Hi, this is your instructor, Mr. Pinter. Welcome to our first video lecture of the course, The Language of Science. This material will introduce you to units and scientific notation. There is not a chapter in our textbook on this material, so use these lecture notes to help prepare you for Homework 1 and Quiz 1. Let's get started. The goal of science is to understand the natural universe we live in. So there are sort of two parts of this. The first one is that we need to describe the objects around us in our universe. And so we describe things by, for example, their size, their mass, color, temperature, composition, etc. Whatever we use to describe something, we're going to require units of measurement. So the second part is we need to find relationships that describe how objects interact with each other. And these relationships in physical science are usually defined through mathematical equations or formulas. So later on in the course, for example, we will learn about the Newton's second law of motion, which says that F equals ma. So this is a relationship between the force acting on an object, the object's mass, m, and a is for the acceleration of the object. So this is an example of one example of many that we're going to see in this course that describes relationships between various quantities. So in this, this is a relatively short chapter, but what we're going to do is get started with our study here, and we're going to learn about units and also numbers in science using scientific notation, and also just a quick basic review of algebra so that we can solve equations and formulas like the one I mentioned up here. So let's get started. So let's start by talking about pure numbers versus numbers used in science, which represent physical quantities. So, for example, in math class, you're almost always dealing with pure numbers. So if we, add 1 plus 1 to get 2, these are just numbers that we're adding here. The square root of 9 is equal to 3. This is another relationship between numbers. Or maybe we have an algebraic expression like x plus 2 equals 5, where we have to solve for x here, and we find that x is equal to 3. But again, these numbers don't necessarily represent anything here. They are just pure numbers. What we're dealing with in this class is physical science, which deals with numbers that represent physical quantities that require units which tell us what the numbers mean. So for example, if someone asks you, what is the length of your car? And you tell them 4.6, well, that's meaningless because 4.6 what? 4.6 inches, 4.6 miles. Well, we're going to use, for length and distance in this class, we're going to use the unit of meters. But so we could describe the length of a car as 4.6 meters. So here the number 4.6 represents something physically. It's not just a pure number, and it's not a number because it's attached to the units of meters. Likewise, the time to eat a snack, 60 seconds, so this tells us the unit of time. The mass of a bicycle might be 12 kilograms. So these are three commonly used units that we're going to be using quite often in this course, and we're going to see many other units as well as we go through the course. Most of what we're going to do in this course is using a system of units called SI units, which is actually French for International System of Units. And these are also known as the metric system of units, which you've probably heard. So I'm just want to briefly introduce this system of units. We just mentioned on the last slide, for length, distance, or height, we're going to almost always use the meter. And the meter has a symbol of m. For time, we will measure time in seconds. Now, sometimes we may see times listed in minutes or even hours, and in that case, we may have to convert to seconds to do our calculations. And the symbol for the second is just an S. We'll introduce the concept of mass later on, and mass is measured in kilograms. The symbol here is kg, and we'll learn shortly what this prefix here, kilo or kilo, means 1,000. So this is actually 1,000 grams. But the unit here of mass is not the gram, it's actually the kilogram or kg. For volume, there are a couple of metric units. One of them is the liter, which has a symbol of L, and the other is the cubic meter, or meters cubed, as is shown here, meters to the third power. Later in the course, we'll learn about force, and force is measured in units of newtons, which is symbolized with an N. And for Newton, energy will be measured in units of joules, which has a symbol of J. Power has the unit of watts, which has a symbol W. And so this is just it's actually kind of a short list. We're going to learn about quite a few units in this course, but this is gives us an idea of sort of what we're dealing with here. And again, the kind of the main message here is that when we study science, particularly a physical science like this, we need to measure and quantify things, and in order to do that, we need to assign units to the numbers. Oftentimes in a science class, we deal with numbers that are either really big or really small. For example, later on in this course, we'll be learning some things about astronomy, and we're going to be dealing with huge numbers in the billions or even trillions. Also, in this course, we're going to be dealing with things that are extremely tiny. For example, we're going to learn about the atom, and we're going to learn about the nucleus of the atom, where things are extremely small numbers. So in this, because these numbers are difficult to write out when they're really big or really small, because there's so many zeros, we use something called scientific notation, which I'm sure you've seen before. You probably learned about scientific notation in high school. Scientific notation is based on powers of 10. And so this is just sort of a review of scientific notation, but we need to make sure that we are fluent in using scientific notation because, as I mentioned, we're going to be using it quite a bit to describe things in this course. So the powers of 10 means that 10 to the first power is just 10. 10 to the second power, or 10 squared, is 10 times 10, which is 100. 10 to the third power is 10 times 10 times 10, which is 1,000. 10 to the fourth power is 4 powers of 10, which is 10,000, and so on. So you can see there's a pattern developing here. The power of 10, the exponent here, tells us how many zeros there are after the 1. So 10 to the first power, there's 1 0. 10 to the second power, there's 2 zeros. 10 to the third power, 3 zeros, and so forth. Down here where we see 10 to the sixth power, which is 1 million, by the way, that is a 1 followed by 6 zeros. So instead of writing out something like this, 1 million with all these zeros, we're just going to say 10 to the sixth power. So this system here can be used with any number. It doesn't have to be just a power of 10. So for example, let's say we want to take this number, 300, and convert it to scientific notation. So 300 is 3 times 100, and remember 100, we can look up here, is 10 squared. So we can write 300 as 3 times 10 to the second power. The number 420, well, this is a little different. We have this, we're still going to use 100 as our multiplier, but now we have 4.2 times 100. And so our number in scientific notation is 4.2 times 10 squared. Now, the main convention for writing numbers in scientific notation is to always have one number over here on the left, to the left of a decimal point, and all the other numbers are decimals after the decimal point. Okay, so like this, let's take this next number, 6,273. What we do, remember the rule is we have one number in front of the decimal point. So we have 6.273, all right? We put the decimal point right here, and then we have to multiply that by 1,000, right? Because we're talking about thousands here. So our number is 6.273 times 10 to the third power. This number here, this is actually 7,500,000,000, all right, lots of zeros. Well, the rule again is we put the decimal point after the first number here. So we put it after the 7. So we have 7.5, and what we can actually do here is you can count how many zeros or how many places go after that. In this case, it is 9, so it's 10 to the 9th. So this number is written, is expressed as 7.5 times 10 to the 9th power. Another way to think of this, if we go back to this number here, 6,273, one thing we can do here is, remember, we're going to put the decimal point after the 6, all right? We always put it after the first digit, and then we just count how many we have to go over. So we count 1, 2, 3 to get to the end of the number, and that tells us that it's 10 to the third power. So in this one here, we're going to put the decimal point after the 7, and we have to now count how many places to go all the way to the end. So we count 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's how I get 10 to the 9th power. Now we can of course work backwards. By the way, these numbers here on the left up here are called expanded form, and the numbers on the right that we converted them to are, in scientific notation. So now we're going to work backwards. We're going to start with a number in scientific notation, and we're going to write it in expanded form. So if we have 5 times 10 to the third, well, we can just write that as 5 times 1,000, using this here, 10 to the third is 1,000, which is 5,000. If we have 1.3 times 10 to the fourth, that's 1.3 times 10,000. Okay, and that is equal to 13,000. If we have something like this, 8.79 times 10 to the sixth, well, we can write, there's two ways to do this. We can write it as 8.79 times 1 million, right? 10 to the sixth is shown right here as 1 million, and that's 8,790,000. The other way to do this is we can start with this number here, and we know we have 6 0. We have to move the decimal we have to move the decimal point here 6 places to the right. So if I start here where the decimal point is between the 8 and the 7, I count over 1, 2, 3, 4, 5, 6, and then I fill in all those spaces with zeros to get the same result here. So the previous slide dealt with scientific notation for large numbers. We can do the same thing for small numbers. And here again, we're going to use powers of 10, but notice here the powers of 10 are negative. So 10 to the negative 1, remember a negative exponent is the same as a reciprocal, meaning this is 1 over 10 to the first power, which is 1/10 or 0.1. 10 to the minus 2 is 1 over 10 squared, which is 1/100th or 0.01. 10 to the minus third is 1 over 1,000 or 0.001. So again, you can kind of see the pattern developing here. Basically, the exponent here tells us how many places the decimal has moved over. Okay, it's and so we fill those in with zeros. So 10 to the minus 6 down here is 1 millionth. So there's a decimal point here, and now we have 5 zeros because if we count over 6 places, 1, 2, 3, 4, 5, 6. We always have the decimal point over here to the right of the 1. So let's convert some numbers from expanded form to scientific notation again. So the number 0.03, well, that's 3 times 0.01, all right? I'm just multiplying these together here. And so that can be written as 3 times 10 to the minus 2. There's another way to do this. We can just start with our pointer here at the decimal point, and notice we have to move the decimal over to the right 2 times to get it after the 3. And so that tells us what the exponent is here. It's minus 2. For the number 0.042, again, there's 2 ways you can think of this. It's either 4.2 times 0.01, which is 4.2 times 10 to the minus 2, or again, we can take this decimal point, which is right here, and we can move it over twice to put the decimal between the 4 and the 2, where it is here. And that moving the decimal twice means we have 10 to the minus 2 power. This one here, 0.0006273. Well, I'm showing how to do that here. What we can do is count how many places we have to move the decimal so that it ends up between the 6 and the 2. So we move it once, twice, 3, 4 times. So we have 6.273 times 10 to the minus 4. The number 0.00000075, that's the same as 7.5, and we have to think about how many places do we move that over. Well, we're starting here. We're going 1, 2, 3, 4, 5, 6, 7 places over, so that's how I have 10 to the minus 7 there. And of course, we can work backwards. We can start with a number in scientific notation, and we can write it out in expanded form. So the number 5 times 10 to the minus 3, we can write as 5 times 0.001, which is 0.005. The number 1.3 times 10 to the minus 4 is 1.3 times, and we can look up here on the chart, 10 to the minus 4 is 0.0001. And multiplying those together, we get 0.00013. Let's do another one, and I'll show you, kind of a trick again. If we have the number 8.79 times 10 to the minus 6, well, one way to write this is start with the number here. Here's our original number, 8.79, which is this number here. And we have to move the decimal place 6 places to the left. So what I do is I count over 1, 2, 3, 4, 5, 6, and put the decimal right there and fill in all the zeros there. So I end up with 0.0000879. Here's a couple more examples using scientific notation. So these on the left here are to start with an expanded form here and write them in scientific notation. So this number given here, this is actually 213 million. One way you can think of doing this again is the decimal is over here. You can think, all right, well, if I'm going to move that decimal point between the 2 and the 1, I have to move it over 8 places if you count. So it's 2.13 times 10 to the 8th. Likewise for this number, 0.00872, if the decimal place is right here and I need to move it between the 8 and the 7, then I need to move it 1, 2, 3 places, so it's 10 to the minus 3. Working backwards, expressing in a scientific notation in expanded form, so the number 5.6 times 10 to the 4th, we're starting with the decimal place here between the 5 and the 6, and we're going to move it over 4 places. So we have to pad those places with zeros to get 56,000. Likewise, 9.71 times 10 to the minus 5, the decimal point is originally between the 9 and the 7 over here, and because it's a negative exponent, we're going to make this a smaller number, so we're going to move the decimal point to the left 5 places, filling in the zeros. So you may have learned, your own methods of the tricks of how to write numbers in scientific notation, but usually it's a matter of either looking at the table or just counting the decimal places. One thing I would highly recommend and almost demand for this class is that you get yourself a scientific calculator. This doesn't have to be a big investment. And it doesn't have to be a fancy programmable graphing calculator or anything like that. The one I like to use is a Casio FX260. It's a solar powered calculator. It has the solar panels right here, so you never need batteries for it. It just runs on light from in your house at your desk. And the great thing is the price, you can get them for about $7, for example, on Amazon. But it's a scientific calculator, so it has all of the scientific functions that we're going to need for this class, and you can certainly use it for your other classes as well. So regarding scientific notation, you'll have to learn how to use whatever calculator you end up buying. You may already have one from high school. Be sure that you know how to use scientific notation on this calculator. Let me show you an example here for this particular calculator. If you wanted to type in the number 1.5 times 10 to the 5th, the way you enter that in this calculator is, you would push 1.5, and then to get the exponent, you press this key down here. On this calculator, it's called EXP for exponent. You press that button, and then you would enter the 5 up here. You notice you don't have to put the 10 in there. You just enter the power, and it looks like this on the calculator. It's 1.5, and this 5 up here tells you the power of 10. So this number here is actually this number here, 1.5 times 10 to the 5th power, which is 150,000. All right. On your calculator, it may not be called EXP. I've seen some calculators, it's called EE. Again, your job is, if you don't get one of these calculators here, if you have a different calculator, you absolutely need to figure out how to work with scientific notation. Another example here, if you wanted to enter the number 1 times 10 to the minus 3, you would enter, again, 1.0, press the EXP button again, this button down here, and then you would hit this plus minus button right here. This puts in a minus sign. You can see it in front of the 3, and then you enter the 3, which is the power. So you can see here it's 1.0 to the negative third times 10 to the negative third power. So now that you understand how to use scientific notation, we also have to learn how to use it in the Mastering Physics homework and quiz platform, because when you're doing homework and taking quizzes, you're going to have to enter numbers in scientific notation. So these next couple of examples will show you how to do this. So let's just start with an example. Suppose you do a problem, and the answer to the problem is 5.2 times 10 to the 7th. So you need to enter this number in Mastering Physics. This screenshot right here is showing the answer box for a typical problem, either a homework problem or a quiz problem in Mastering Physics. So in order to enter this number here, what you do is you'll see up on the top here, there are these buttons. So the button on the upper left right here, you're going to click on that with your mouse. And when you do that, when you click on that button, you're going to see all of these choices under here, okay? And each one of these has a different function. This one is for an exponent, x to the a. This one is for a subscript. Here's how you make a fraction. Here's a square root, etc. What we want is this last button over here on the right. Notice it says x dot 10 to the nth power. That is the button we're going to use, because what we're going to do is we're going to write this number 5.2 times 10 to the 7. we're going to write it like this, 5.2 dot 10 to the 7. The dot just means multiplication. So what you do is you click on this button here, and when you click that button, you're going to see this come up in your answer. There's going to be a blank here where the cursor is, and then you can see the dot, and you can see the 10, and then there's a little blue window up here, which is basically asking you to enter a number. So what you would do, since the cursor is right here, this is the cursor, this little blue line, you're going to type in your 5.2 right out in front here, and then with your mouse, just click on this little blue button up here to get the cursor up in the blue window, and you can put the exponent, which in our example here is a 7. So you would just type the 7 here, and there is your final answer in scientific notation. And then the last thing you would do is hit the submit button, which I did not show here. Let's take a look at one more example. So in this example, very similar thing, except this time we'll do a different number. This one is 3.57 times 10 to the minus 3. So again, you're going to start by clicking on this upper left-hand button here, which is going to give you all of these choices. And again, you're going to click on this button on the right now, which is the scientific notation button, x dot 10 to the nth power, which is going to give you this here. And now all you have to do is type in our 3.57 out in front, and then put your cursor, click on that little blue window for the exponent, and type in negative sign and 3, and there is the final answer. Have a calculator that you're going to be using. I want to show you some arithmetic practice that I want to make sure that you can do these problems on your calculator. So even though these may look really simple and basic, make sure that you can do all these problems here and get the correct answer, because this will ensure that you're pressing the right numbers and the right order on your calculator. So, you know, for example, this is 14 times negative 3. You should get negative 42. And again, the way you put negative numbers in on this particular calculator, you use this button right here, the plus minus button, to make, you know, you would press that before you would put in the 3. This is another one that a lot of students make mistakes with. That if you have an expression 84 divided by 12 times 3.5, all down here in the denominator, do this on your calculator and make sure you get the correct answer of 2. A lot of students will type in 84 divided by 12 times 3.5, and that is not correct. The correct way to do this on your calculator is 84 divided by 12 divided by 3.5, or use parentheses around these two numbers if you're going to multiply them. So either way, make sure that you get this right number so you don't make this mistake on the homework or on a quiz. Know where the square button is. All right, 75 squared. On this calculator, you can see it right here. It says x squared. So that's the number you press to square something. Likewise, find out where the square root button is. Make sure you can figure out the square root of 75. On this calculator, you'll see it right above the square button. So to access the square root, you press Shift and then the square button. That does the square root of this number 75. The reciprocal button is sometimes useful. So you can tap in 0.32, and then if you look here, let's see, I need to find it here. It looks like it's right here. This 1 over x on this calculator is here, but you know, again, this may be a different button on your calculator that you're going to use. But that button takes the reciprocal of whatever number you put in there. Another one that you're going to need to use is the power button. So if you want to do 15 to the 3.5 power, this is the correct answer, by the way, make sure you can do this on your calculator. On this calculator, that is done here with the x to the raised to the y power. So you would actually type in 15, press this button, and then type in 3.5, and then, you know, the equal sign. So, you know, you might want to be pausing this video right now and go through these and make sure you're getting the right answer. If you're not, please figure out how to do these correctly on your calculator. Ask for help, or you can ask me if you can't figure it out. Scientific notation, make sure that you can do these problems on your calculator using scientific notation. And what makes some of these tricky is there are minus signs. This one has a minus sign in front of the number out front. This one has a minus sign here, and it has a minus sign in the exponent. And so make sure that you can add, subtract, or multiply, or even divide. This is a division problem down here in scientific notation, and make sure you're getting these correct answers. So this will, it sounds like, a little bit of busy work right now, but make sure you can do these problems on here, and this will save you a lot of headache later. Let's now talk about what are called metric prefixes. So this is a table here that shows a list of most of the metric prefixes. There are others, they keep going past what this table shows, but those are used much more rarely. So for example, the prefix deca means to multiply by a power of 10. So in other words, a decameter is 10 meters. All right, a decaliter is 10 liters, and so forth. A decagram would be 10 grams. And you can see that, the prefix is deca. It has a symbol here, DA. This one is not used, surprisingly, this one is not used that often. Likewise, there's one called hecto, which means 100. So a hectogram is 100 grams. Kilo, this is one that's used a lot. Kilo is 1,000. So a kilogram or a kilogram is 1,000 grams. Okay, a kilometer, or we say kilometer, is 1,000 meters, etc. And kilo, you can see, has the symbol K. Mega is another one that's used quite often. Mega means 1 million. That's 10 to the 6th power. And mega has a symbol of an uppercase M. It's important to use the right case here. It's case sensitive because notice lowercase m means milli, which is 1,000th. So that's very different than mega, which is 1 million. And then it goes up from there. Giga is for a billion, and tera is for a trillion, which is 10 to the 12th power. And then we can also use these prefixes for smaller quantities. For example, deci, not to be confused with deca, is 1/10. So a decigram is 1/10 of a gram, a deciliter is 1/10 of a liter, etc. Centi, that one is very common. For example, the centimeter, right, is 1/100th of a meter. So centi means, or has a symbol of lowercase c. Milli, as I mentioned before, it sounds like that would mean 1 millionth, but it doesn't. It means 1,000th. It's 10 to the minus 3rd power, and milli is abbreviated with a lowercase m. Micro, which is 1 millionth, actually has a Greek symbol. It's the mu symbol. The lowercase Greek mu stands for micro, which means 1 millionth. So a micrometer, for example, which is also called a micron, is a unit of length equal to 1 millionth of a meter. Nano, you've maybe heard that one. That is for something that is 1 billionth. So a nanometer, which is something that we're going to use to measure the wavelength of light, is a very small unit of distance. A nanometer is 1 billionth of a meter, and a nanometer would be abbreviated NM. And the smallest one I show here is pico, which is 1 trillionth, 10 to the minus 12. So let's just do a couple examples here so you get the feel of this. So 2 kilometers. Well, kilo, remember, that means 1,000. So first of all, we can...
having some trouble with the connection.
Oops, excuse me. We have 2 kilometers. Let's abbreviate this first with K for kilo and M for meter. So 2 km, or 2 kilometers. Well, remember, kilo is 1,000 from up here in the table. So that's 2 times 1,000 meters, which is 2,000 meters. And if we want, we can even write that scientific notation as 2 times 10 to the 3rd meters. 5 centimeters or 5 cms. Well, a centimeter is 1/100th of a meter, so it's 5 times 0.01 meters, or 0.05 meters, which is 5 times 10 to the minus 2 meters. 15 milliseconds, or 15 ms. Well, remember, milli, if we look up here in the table, is 10 to the minus third, or 1,000th, 0.001, which I wrote here. So this is 0.015 seconds, or in scientific notation, 1.5 times 10 to the minus 2 seconds. 3 nanometers, or 3 nm, is, again, a nano, remember, is 10 to the minus 9. All right, or 1 billionth. And so this is going to be, we're going to have all these zeros here. So we have, this is 3 billionths of a meter. Or we can write it in scientific notation as 3 times 10 to the minus 9. I think I have a typo here. This should be a minus 9. Sorry for that confusion there. Let's do just a couple more here. 14 megaseconds. Well, remember, mega means 1 million, so this is 14 million seconds, or 1.4 times 10 to the 7th seconds. 4.2 gigawatts. Well, giga, we can look up here, that is 1 billion, all right, or 10 to the 9th. So we can write it as 4.2 times 10 to the 9th watts. So let's just do a very quick review of algebra. The reason for this is that mathematics is a very powerful tool to use in physical science, especially in a science class like this, a physical science where we are going to rely on measurements and data and quantitative data to describe things with numbers. So we're going to need mathematics. In fact, we'll learn later that Isaac Newton actually invented calculus to help him solve physics problems that he couldn't solve with algebra. The good news for us is that we won't have to use any calculus in this class, but we will be using a lot of algebra, and we'll be doing algebra in just about every lecture in this course. So this is not a math class, so I'm not going to go through a bunch of algebra with you guys, but I would like you to just do some quick review. These are 4 problems here that you should be able to solve using really basic fundamental algebra that you learn in high school. So if you see something like 3x minus 2 equals 7, you should know how to solve this, right? You have to get the x all by itself, so you can add 2 to both sides, to get 3x equal 9. You can divide by 3 to get the answer x equal 3. So make sure you remember how to do this. This expression here, d equals 1/2 at squared. This is actually a formula that we're going to encounter pretty early on in the course. You should be able to solve this for t, which represents time. And to do this, again, you have to get the t all by itself. Get rid of the 1/2 by multiplying by 2. Divide by a, and then take the square root. So you should get t equals the square root of 2d divided by a. Something like this expression, mgh equals 1/2 mv squared. You should be able to solve this for v. All right, even though we don't have any numbers in here, you can still solve it. You should be able to realize that you can simplify this by canceling the m's on both sides, and then isolate the v squared, take the square root, and you should get v equals square root of 2 times g times h. And then something like this, we're going to encounter this equation later on in the course. P squared equals r cubed. You should be able to solve for both p and r, and those expressions are shown here. We'll actually go over this one a little more carefully later on in the course, but you know, these are the types of basic things that you'll need to be able to do to be successful in this course. So if you're, you know, rusty on your algebra, or if algebra was not your strength in high school, don't panic or you know, get too stressed out yet. We're going to take things slowly in this course, and I guarantee you by the end of the course you will certainly be much stronger and better at math, in particular in algebra. The last slide here in this, our first lecture here, is about graphing, and you're going to certainly have to be able to interpret graphs in this class. Because of the online nature of the class, you may not be making any graphs per se, but you'll have to know how to read them and so forth. So let's just take this example here. Let's say you take a hot cup of coffee and you stick a thermometer in there. It's a Celsius thermometer. And you measure the temperature, you know, right after you pour the coffee, and then every 5 minutes you take and record the temperature of the coffee, and you do this for 25 minutes. So what you end up with is some data. For each time, you know, 0 minutes, 5 minutes, 10 minutes, 15 minutes, 20 minutes, 25 minutes, you're going to measure and read a temperature here and record this. So let's say then we graph the temperature here as a function of time, and we can see that what's happening here is the coffee starts out at 90 degrees. After 5 minutes, right, this is the time down here, it's dropped to, it looks like 55 degrees. After 10 minutes, it's dropped to about 32 degrees. And then after 15 minutes, it's at 20 degrees, and so on and so forth. So this shows the trend of the coffee cooling until it reaches basically room temperature here, which looks like about 18 or 19 degrees Celsius. And then the temperature is stable. So this graph has a lot of the characteristics of a well-made graph. So let's just look at these real quickly. So a good graph should have a title. So the title is a description of what this graph shows. This graph is showing us the coffee temperature versus time. So the coffee temperature is this axis here as a function of the time down here. So the independent axis label, that's this here. So this is, notice this, we know what this graph refers to down here. It's time, and it's very important, of course, to have the units. The units here are minutes. These are not seconds or hours or days. Likewise, the dependent axis label, that's the one over here on the vertical axis. This is called a dependent axis because the temperature depends on the time. The time is an independent variable. That, you know, time just keeps ticking along, all right? That's the independent variable. The temperature depends on the time. So this dependent axis also should be labeled. We're talking about temperature, and the units here are degrees Celsius. And typically, again, those units are put inside parentheses, like you can see here. Notice that both axes are scaled with tick marks and which have numbers. So we can see that, you know, this is 5, 10, 15, 20. The temperature is going up by 10 degrees, 10, 20, 30, 40, 50, etc. Data points are clearly shown. Those are the black dots there. And optional on this graph, which is nice, we can see grid lines, this sort of checkerboard here. You know, if you're using graph paper, obviously those are going to be pre-made. And then the other thing that's an option here, but it's nice, is a trend line that connects the data points. So in this case, there's a nice smooth curve that connects and shows, this sort of interpolates what the temperature would be in between our data points. We're sort of guessing that this would be a smooth curve like this. So this is an example of a nice graph. It's very clear, and you know, everything is labeled correctly. It's very easy to interpret a graph like this when it's made correctly. So one of the first things we'll be doing in this course, in our next lecture, as a matter of fact, is learning how to graph motion, and we'll be constructing graphs, you know, somewhat like this, to analyze the motion of an object. So that's it for Chapter 2. I will see you shortly when we begin Chapter 3. Goodbye.